Prof introduce Mark Bowick.
Thank you very much. Can you hear me? Okay, good. So I'm a director of soft matter program at Syracuse University, and we have 4 theorists, myself, Christina Marchetti, Lisa Manning, and Jen Schwartz, and we interact strongly with Alan Middleton as a condensed matter theorist in our group, and then people in Syracuse Biomaterials Institute and chemistry, biology, and so on. And we have a website there and Facebook page, and we have postdoc positions. That's most important. So if you're students or postdocs looking for jobs, contact me or any of us. Okay, so today I would like to talk about the origin of shape or certain kinds of morphology in soft systems, in liquids essentially, but liquids with the kind of order that you love, that this program is all about, namely a liquid crystalline order. So more specifically, these will be shells, molecularly thin shells of liquids, namely vesicles. Okay. So they will be built of soft stuff, actually this kind of stuff here, which is a bulk liquid crystal, in this case smectic former, but could be a pneumatic former as well. And we'll see how that's used. And what I want to show is that you can get structures that are more reminiscent of hard materials, that look like gemstones, that look like this kind of thing or this kind of thing, or a diamond ring, namely polyhedral faceted objects, two-dimensional objects, which is talking about the surface of the polyhedron. Because of competition between liquid crystalline energies, Frank energies, and bending energies, things that change the shape of the structure in the embedding space, which will just be a three-dimensional Euclidean space in this case. More specifically, we're going to get this kind of structure, the simplest platonic shell, tetrahedron, which is pretty surprising. And we're going to get it in the soft bending energy limit. It's easy to bend the thing. It makes sharp, singular structures, sharp edges and sharp vertices. Okay? So that's the idea. Here's an ancient tetrahedron from Scottish stones, and shapes have inspired people from all kinds of fields since the beginning of time, particularly in architecture. Form, shape, function has a lot of similarities of the kind of things we think about in the physical sciences. Here is a design from a San Diego architecture group of a skyscraper condominium tower complex. Each condominium is a tetrahedron. Okay, so you live inside this beautiful tetrahedron here built up. The simplicity of that building block inspired them in this case, and I want to show how you can get that building block in a rather surprising way. This is Newton Institute. What I'm interested in actually more generally is unusual minima, unusual ground states, unusual solutions of analysis problems, unusual minimizers. In this case, we're going to be talking about shapes, say optimal shapes. Newton in the Principia considered a simple problem like this: optimal resistance. What is the shape, the front of a train that minimizes the resistance? He took a very simple example of resistance, just a body moving in one direction straight into an inviscid fluid, and the resistance is just due to a single molecular interaction, single molecule bounces once and comes off. So in that case, you can derive what's called sine squared theta law for the momentum change due to the impact, and you get a formula for the resistance, and it goes like 1/1 plus the square of the gradient, absolute value of the square of the gradient of the profile. So you already see there because of their gradient appearing in the denominator, that kind of rapidly varying profiles can lower the resistance in some cases. So he showed, the semicircle hemisphere is half the resistance of flat front, but the solution, the optimal solution, and he assumed radial symmetry. So you have a function valued across this domain here. It has some size r, some diameter, and it has some maximum height value of the profile, m, say. If you assume it's radial symmetry, simplest thing to do, physicists like to exploit symmetries of these problems, but that can lead you badly astray. You get, depending on the height, some rather interesting solutions. Here's the height is 1/2 the radius, and you see you have a flat, snub-nosed front. Okay, so you already see something singular happening here. The derivatives are discontinuous. But Kewal and a couple of other mathematicians showed a while ago that these are not optimizers. Restricting to the radially symmetric functions is not going to give you an optimizer. You can do better if you abandon radial symmetry. And the radially asymmetric solutions are not completely classified, but they've been studied by a variety of groups. Here's a paper by Lachand, Robert, and Pelletier. And you can get, depending on this height divided by the radius, really weird solutions. So, chisels like this, one sharp edge, triangle, polyhedral faces with sharp vertices as well, square, polygon, and so on, depending on m over r. And the exact optimizers.
Is this resistance calculated for inertial particles?
Yes.
For inertial.
Yes, inertial particles, constant velocity, no viscosity, one bounce. Okay.
Where are they attacking it from?
Along the direction of motion.
Yeah.
Going along like this.
Where is that on your diagram? Where that blue is?
So up, so that's vertically. It's moving like this.
Right.
So this will be the front of your train.
Right.
You might see a Japanese train one day with them. People have also analyzed the conditions under which this approximation is good. Actually, it's good in some surprisingly interesting situations. But what I wanted to show here is that symmetry is not always a good guide, and the optimizer can have rather interesting behaviors, sharp behaviors here. That's the idea. Let's turn to, this is one other example that I've spent a lot of time working on of unusual ground states. This is the crystalline order on the surface of a ball, two-dimensional sphere, for particles interacting pairwise with a power law potential. In this case, it's Coulomb. Okay. There's 3,000 particles on the sphere. You have to have some topological defects because of the topology of the sphere, namely some 5-fold coordinated points, disclinations, but the actual ground state above a few hundred particles has extended defect structures that we call scars. So this was studied by Alex Travisette, David Nelson, and myself starting in 2000. So here this 5 is extended, 5, 7, 5, 7. Well, you can see it here, 5, 7, 5, 7, 5. Extended defect with one net 5. So the disclination spreads out into a linear object instead of a point-like object. So it's shown a little bit more clearly here. This is energy map. This just shows the triangulation with the defects marked. So that's quite a surprising ground state. It has extra topological defects not required by topology in the ground state. It occurs to minimize the energy. It's a property of the minimizer, unusual structures in the ground state. Let's turn to shape and condensed matter, soft matter systems. Soft matter is fantastic because unlike the large-scale structure of the universe, which is spatially flat to a very, very high degree of approximation, and topologically trivial, all kinds of interesting curved structures occur in soft matter, and interesting topologies as well. I'll focus today mostly on shape. Here is the viral capsid of a bacteriophage, HK Hong Kong 97. Yeah. And you see that it takes a faceted icosahedral-like shape, small viruses are kind of round. Large viruses are above a buckling transition, and they tend to facet into these kinds of icosahedral shapes. This happens actually after they're built, and then they package DNA inside afterwards, and the buckling occurs as they push the DNA inside the viral capsid. Here's one of my favorite viruses. This is the adenovirus, very common, responsible for lots of respiratory diseases and so on. It has this kind of shape as well, but it has 12 disclination defects, 5s, shown as the dual pentagons here, and each 5 is biologically functionalized by a fibril that comes out from that 5, and it's used to latch on to cells. So that's another cool thing about these things. You can use this functionalization for supramolecular chemistry, use these objects as building blocks of molecules and bulk materials, but biology also does it naturally. Here is a really cool example from the group of Monique Dubois at Saclay from 2001. They looked at salt-free mixtures of cationic and anionic surfactants, they're called cat anionic systems, and showed that as you cool them down through a chain melting transition, they also facet into icosahedra. Here's a freeze fracture shown on the left, and you see a very beautiful 5-fold coordinated object vertex here with a dual pentagon here. If you take a cross-section from freeze fracture based on a vertex, you see that. If you go through the equator, you see it in projection with electron microscopy. That's shown here, but you can't see it very well. It looks hexagonal. The icosahedron is the basically unique object that does that. So they can reconstruct that the thing is icosahedral, and furthermore, they can show that there are pores, 15 nanometer pores, holes at the vertices. Okay? And so you can get material in and out through those holes. So here it goes from not being a sphere, it's something with Euler characteristic -10, a sphere with 12 holes or boundaries in it. And this probably occurs because of charge effects and so on. This seems to stabilize the icosahedron. Icosahedra are not that common even in hard, crystalline-like materials. They're very unusual. So it's very nice that you can make them here. You can look at elastic membranes, if you want, things with stretch and shear moduli and bending deformations into space, but with 2 components. So this was studied by Vinicius Konepnik and Monica Olvera de la Cruz. They considered 2-component systems. As you know, if you have more than one component, that's where you get frustration, interesting things going on and so on. So they looked at a thing that's hard to bending, stiff and soft to bending, things with 2 different bending rigidities. The red is hard to bend, stiff, and the blue is soft. And you can get structures that have these kind of flat faces and a lot of bending along the soft component. There's a lot of beautiful things that can go on with pneumatic elastomers and pneumatic glasses. So here's something shown from Carl Modis, Bhattacharya and Mark Warner here. If you have pneumatic glasses and you heat them up and down and you have defects in it, then the preferred shape can be very interesting to accommodate the pneumatic order and the bend and the defects. What I want to talk about, as I said, is liquid crystalline vesicles. Okay? So there's a microscopic sacs, here's a macroscopic example, that enclose a volume and they're molecularly thin in our case. So this orange mesh is going to be some, few nanometers in thickness. So we'll be able to treat it as a 2-dimensional object, but embedded in 3 dimensions with the bending energy and some kind of order along the surface, 2D order. Thin enough, we can treat it as a 2D problem. You can, of course, make these things from amphiphilic bilayers, like lipid bilayers, and you get liposomes. The realization I'm going to talk about today uses block copolymers. They're like amphiphiles, with a head and a tail, covalently bound together. and they can make polymersomes analogous to these liposomes. In fact, when I was on leave in Paris a few years ago, I hooked up with a very good polymer chemistry group at the Curie Institute, particularly Min-Hui Lee here, the polymer chemist, and they were making interesting vesicles from block copolymers of a certain kind. You have a lot of richness when you work with block copolymers because you not only have the A, B part of the block copolymer, shown here as a blue, in this case it's PEG, coil-like head and a rod-like hydrophobic tail. What you can do is do chemistry, build in functionality, in particular liquid crystalline order, in this case into the hydrophobic rod. Okay? There are liquid crystal mesogen side chains in this system. They choose bulk liquid crystal formers for these mesogens, but if you do it right, you can make a vesicle where that liquid crystal order goes over into the surface of the vesicle as 2D order rather than 3D order. So here's one of the block copolymers they use, the PA-col. This just shows the bulk phase diagram. It has an isotropic, high temperature isotropic phase. In this case, an intermediate smectic phase. It's actually an interdigitated smectic phase, as you can see here, and low temperature glass phase. It forms bilayers. Here's shown cross-section through the bilayer. And miraculously enough, this is not 100% understood, you can make a 2D smectic. So that this order, this interdigitation and so on, this lining up extends right through the 2D shell. So what you get is a striped 2D smectic vesicle, constant layer spacing object on the 2D surface. This spacing here between the layers, this fixed layer spacing smectics, corresponds to the bulk spacing of the 3D smectic former. We're not going to analyze here exactly how this forms. Interesting symmetry breaking and so on going on here. We're going to assume we have a 2D liquid crystalline vesicle and ask about its shape. But here's an image, electron microscopy image from one of these vesicles. They make giant unilamellar vesicles, microns in size, 10 nanometers or so thick, and it might be a little hard to see, but if you see it close up, it has stripes across it. It's definitely a smectic, and that can be established. Here's one of the images they showed me one of the reasons they called me in to look at this. Some of the vesicles have very angular projections like this kind of shape. How can you get that? That's what we're interested in. This is the vesicle here, and it's sitting on electron microscope grid. So it's just one vesicle. This is not another vesicle. This is just the grid, part of the grid. Okay, so Homan Shin, Jianjun Jing, and Jinwei Yao and I analyzed this problem. So let's start first of all with the monolayer. Okay. So we will have some 2D Frank energies shown here, discuss in detail this term in a minute, and a bending energy, and we're going to integrate over some surface that's yet to be determined. This is the challenging thing in this problem. You have free energy where you're also optimizing over the 2D manifold that you're integrating over. Okay? This is so you not only have to find the preferred order, but you have to find the preferred surface. Each one of those problems is tough. The liquid crystalline order is very interesting, even in the plane. But here it's bending in 3D, and we don't know what surface it is. Actually, you can treat, So here we'll treat two different problems simultaneously. We simplify by taking just one bending rigidity. There are actually three independent bending rigidities because this couples to mean curvature tensor. It's three components. And there can be, in this monolayer case, three components of the spontaneous curvature. I'm just going to take one bending rigidity. I'm going to take one Frank constant. So this could be either one of two cases. The one Frank constant approximation pneumatic, where the splay modulus K1 is the same as the bend modulus K3, K1 equals K3, in which case it becomes K, and it couples just to the covariant derivative of the director field N squared. That's K for the one Frank constant pneumatic. Or we can take the limit K3 goes to infinity. If we take the limit K3 goes to infinity so that we eliminate bend, we completely suppress bend, then we only have splay for the director or line field. Mathematically, it's a line field. And then we can draw the orthogonal level set to that, and that makes a constant layer spacing object, which is a symmetric. If we have bend for the director field, then the level sets are diverging, and that means the layer spacing is growing, and that's completely suppressed in the limit K3 goes to infinity. So in that case, we're left with just K1, which I'll call a K here. Okay? And it couples. Yes, defects are also allowed. Yet another wrinkle in the problem. In fact, defects will be essential. I will go in a minute. Yes, 2 dimensions, and I will actually go, and you'll see why, you know why, but you'll see why to the sphere in a minute. So defects will be required, in fact, inevitable mathematically, and will always form, have to form. And they will play some role, some important role. Okay, so keep this in mind, okay? I'll probably most commonly use the symmetric realization because it's a little bit easier to discuss. So you can think of a ruled object, okay? Not ruled in the mathematical sense, but ruled in physical sense. Constant layer, constant spaced lines ruled on the surface. But you can equally well think of the one Frank constant pneumatic. K3 goes to infinity case is very interesting here. When the curl of n vanishes, in two lines you can show that then the covariant derivative of n, the director along n, has to vanish. That follows from n being a unit vector and from curl of n, covariant curl of n, vanishing. So n is in fact an integral curve. It has a priori one component since it's a two-component object that's unit length, but setting curl of n 0 completely determines it. It's completely determined, and just integral curve follows geodesics on the surface. So once you know the space, you know the symmetric layers in this object. If you minimize the free energy for this one monolayer case, clearly, because you have covariant derivative of n here in the free energy, you want the system to be flat. Okay? Any texture for n or any curvature will contribute to the covariant derivative, so that will hurt you. So this means Gaussian curvature must vanish. You have only what are called developable surfaces, those for which the Gaussian curvature vanishes. So those that can be constructed from a flat sheet, just bending, rolling it up, stretching, and so on. So that just gives you the plane, the cylinder, and the cone. And if we have spontaneous curvature, then the only solution is that the mean curvature is the spontaneous curvature. So that will give you a cylindrical monolayer whose radius is 1 over the spontaneous curvature h0, namely a nanofiber. So let's take bilayers. As I said, these are natural amphiphiles. They spontaneously associate to make bilayers. So we'll just take 2 copies of that monolayer Hamiltonian. We're looking at ground states. Well, the free energy is just the energy, Hamiltonian. Take 2 copies of that, and we'll take the simplest case, the symmetric bilayer. That has the interesting structure we want. So the spontaneous curvature vanishes. So I'll put those together, and we have this free energy. Very simple. And this term here, so the field theorists would call this nonlinear sigma model, coupling K, and then we have this coupling to the mean curvature squared. So we have Frank constant, these are energies, and a bending rigidity, also an energy. These two terms will compete. You can, of course, have flat, bilayer, lamellar object. That's fine solution, except it contains a boundary, an edge. Okay? There's edge energy proportional to the length of the perimeter. So when the system gets big enough, it wants to eliminate that edge. This was shown by Helfrich, 74. Okay? So it likes to close up into a sphere, eliminate that edge and its associated line tension and energy. Okay? So we will look at sufficiently large systems. I said they make micron scale structures. Our topology will be that of a sphere. Okay? So let's look closed bilayer polymer vesicle, which is forms topologically two-dimensional sphere, surface of a ball. Now we want the system to be flat, we said, okay? But it cannot be because it's a sphere. The topology prevents the simple solution of it being flat. The integrated Gaussian curvature on the system is 4 pi, 2 pi times the Euler characteristic. We know from Gauss. So we have to get an integrated Gaussian curvature that's big, 4 pi, and we want the thing to be flat. So there's frustration here, there's competition between this liquid crystalline free energy, the bending energy, and the topological constraints. I will discuss 2 limits of this. I call them stiff and floppy with respect to the bending rigidity. Okay? So the stiff limit is when the bending rigidity is large compared to the Frank constant. Okay? So in that case, you basically doesn't want to do anything but doesn't want to deform away from the constant curvature sphere. Okay? So you'll get some kind of deformed round sphere in general. If you put back the anisotropies and so on, the sphere will generally deform to some kind of ellipsoidal shape because of the order that develops on it. For example, if it forms symmetric, then you have these ruled lines on the surface, and it's easier to bend along symmetric layers than it is transverse to those symmetric layers, because bending transverse to the layers changes the layer spacing. So it won't be completely round when you incorporate the symmetric order, and same for the pneumatic order.
If it's made from polymer, which limit is
More appropriate. Okay.
Since these things are molecularly thin and the bending rigidity goes as the thickness cubed, you can realize both limits because you have a lot of control over the relative lengths of the hydrophobic rods and the coil and so on. You can basically realize anything, but you can realize the other limit of very small bending rigidity because it's molecularly thin. Yeah, T cubed as opposed to T. So I'd say actually both can be realized in this system. And they see both. Despite that argument, I don't think the floppy limit that I'm going to describe is more prevalent than the other, surprisingly. But thickness is small, but not trivial. So the limit, this stiff limit, will give you something like a spherical pneumatic or a spherical symmetric. Okay? There's a lot of interesting physics in this case, but I'll discuss the other limit first, okay, because it's most interesting. Basically, and here's a picture of some kind of ellipsoidal symmetric vesicle made from experiments with one of these copolymers called copolymer 2. It's scale bar here is 100 nanometers. So you can see it's microns in size, has stripes, layer spacing 4 nanometers, and deforms away, and you can see the thickness here. So remember, it has actually some variable thickness, which is a complication. It forms one of these deformed spherical-like objects. The interesting physics in this limit has to do with how topological defects, which are required because you're on the sphere, behave differently in the one Frank constant nematic case and the smectic case. In the smectic case, a +1 defect shown here, +1 defect, a vortex, say, for a vector-like field, typically is unstable to forming 2 1/2 disclinations for a nematic, since the energy grows as the square of the strength. But in the limit K3 goes to infinity, a +1 is degenerate with 2 1/2. And in a paper with Jing and Homan Shin a while ago, we showed also that the topological defects behave differently. A +1, shown here, has a 0 mode where you just cut along this great circle, along a director, and slide it by any arbitrary angle to this. This is motion along the integral curve, so it doesn't change the texture of the symmetric or the anisotropic nematic. So this is a completely 0 mode. You can get the you get now 4 1/2 defects living on a great circle with any angle separating them. They all have the same energy. You can't do that for K1 equals K3 or K1 over K3 finite. They'll differ in energy. So we predict that the 4 defects live on a great circle. And Alberto Fernandez-Nieves and his group done wonderful experiments. You can make thin shell nematics, and you can vary K1 over K3, and you can see where the defects are. And in the highly anisotropic limit, you can make these things with microfluidics, one fluid inside another going through a liquid crystal, make a thin shell, and in that highly anisotropic limit, the 4 defects indeed go to a great circle, rather than, in the other case, the 4 vertices of the tetrahedron. That's the interesting physics in that case, but that's not the focus today. The focus today is on shape. There have to be, as Efim was asking, is defects in this system. Here are shown. So I'll just briefly classify structure order on the surface according to its invariance. If you have something like a ferroelectric or a magnet, or wind velocity on the 2 sphere, then you have invariance under 2 pi rotations. I'll call that, so invariance under 2 pi over p, I'll call p-fold order. So this is the case p equals 1, or a spherical ferromagnet. You could make such a thing. You have to have vector fields with zeros. And the Poincaré-Hopf theorem tells you the total index of the zeros of that vector field has to be 2. So you need at least 1 0 of index 2. That would be a dipole. Typically, that breaks up into 2 zeros of index 1. Like here, we have a source and a sink. And same thing for a vortex winding +1 and another one winding +1 somewhere else. And these defects repel typically, so they typically live far apart. So on the sphere, they will be antipodal. For the nematic, we have invariance, a line field, invariance under 2 pi over 2 pi rotations. The +1 can break up into 2 1/2. Okay. Total sum of the strengths of the defects has to be 2 again, so you can have 2 +1s. You can have a 1 and 2 1/2, or 4 1/2. Here's shown a kind of a case of texture of where you have 4 1/2 on the sphere for a nematic, spherical nematic. There's a defect here. There's a baseball texture, and it's been studied by David Nelson in the context of functionalizing this to make a valence 4 type mesoscale or nanoscale building block for molecules and materials. Here's 4, one here, one over here, one here, one here. And this is in Fernandez-Nieves experiments. You see 4 1/2 defects. Eventually, these repel. If the thickness is not uniform, they tend to group because they're actually line defects in the bulk. And so they have some energy per unit length. So where the thing is thinner, they will group. But if you get uniform thickness, they go to the vertices of a tetrahedron. So the +1 like this breaks up into a 1/2 like this, and another 1/2 over here. For the spherical symmetric, as I said, you get this kind of shape. Again, order is p equals 2. Okay, so let's go to this floppy limit. Okay, so it's going to be easy to bend. That's going to be the soft mode of the system. So in the energy, the challenge, the dominant term in the energy, is going to be the Frank term, the liquid crystalline term. Okay? So then you're faced with this challenge of making it flat as much as possible, but preserve the topology of the sphere. So you can do that with a polyhedron. Okay? In fact, here's the simplest example. Just build a tetrahedron on the way you probably did in kindergarten. Just rule 4 triangles like this. In this case, I put on, I'm illustrating the symmetric case. So constant layer spacing, very easy to do in flat space. Just rule it like this. Then fold it up, and it stays. The layers continually cross edges. The layer spacing is constant everywhere. The symmetric energy is identically 0. So you can do this with a thing that's, it's almost flat everywhere. What's not flat, set of measure 0. It's just the edges and the vertices. There are defects. Defects are required. The defects, in this case 4 1/2, are good places also to put the Gaussian curvature. So you also localize the Gaussian curvature. It's concentrated at the vertices. So all the 4 pi is going to be pi at each of the 4 vertices, 0 everywhere. Okay? So it's face-wise flat, almost everywhere in the usual English sense. So this is good. Okay? There's a natural solution to this problem for it to facet like this. I said as a nematic or a symmetric, you need either 2 1s, a 1 and 2 1/2, or 4 1/2. To specify the surface that we're trying to determine in 3D space, we need 4 points to generate a non-degenerate surface. Okay? So we need the 4 1/2 defects actually, and that will enable us to determine a surface in 3D. So the 4 1/2 is the natural solution. It's also physically the most common solution, breaking up into the smallest elementary topological defects. So we have 4 vertices. Each is a disclination defect. Construction is shown here. So if you look along here, you come around, you turn. It's a classic 1/2 defect. Turn 180 degrees and come back to itself, encircling this point here, which will have vanishing order. So 0. How many? So let's work first in the exact bending rigidity 0 limit. Okay? It's a complete 0 energy mode, no bending rigidity. We're just minimizing the liquid crystalline energy, but with the topological constraint. How many ground states are there here? Okay. For a tetrahedron itself, you have 4 vertices. That requires 12 coordinates in R3. It has 3 rotational symmetries, 3 translational symmetries, so that removes 6. That leaves 6 degrees of freedom. And we're interested in shape, not the size of the thing. So there's a scaling symmetry, scale away an overall size. That leaves us a 5-dimensional space of tetrahedra. But this is not any old tetrahedra. It has to realize the symmetric order, and it has to be constructed from flat space in this way. So there's a constraint that you go around 180 degrees around these vertices from flat space. That would give you might think 4 constraints, but actually turns out one is not independent of the other. So there are 3 constraints in order that be a symmetric order on the 2-sphere. So that leaves you a 2-dimensional space of possible tetrahedral ground states for the system. A 2-parameter family. And they correspond to having a not an equilateral triangle, an arbitrary triangle on the surface here, and doing this construction this way here. There will be typically some bending energy. If I put back any non-zero bending energy whatsoever, then I have bending along edges. So that will be, the bending energy will be proportional to the lengths of the edges. The sum of the lengths of the edges then, minimizing that, will give you the regular tetrahedron. And putting back any non-zero bending rigidity gives you the regular tetrahedron as exact ground state for the system. That's quite nice. Remember, in the limit where you make it very, very easy to bend, it becomes sharp in some sense, rather counterintuitive. But that's to minimize the liquid crystalline energy, which is competing with bending and with the topological constraints.
It didn't mean that to minimize the length of the edges in the case that you start introducing some bend, then removes the 2d degrees of freedom that you have surviving after you eliminated all of these.
Yes, you have to have so that you have just a general tetrahedron with unequal edge lengths in the 2D case, 2-parameter family of solutions. You limit that to the regular tetrahedron when you put back bending energy. Remove the degeneracy. Unequal length.
So those unequal lengths were associated with the 2 remaining degrees of freedom?
Yes, right.
Why should that be 2 degrees? I mean, I have no feeling for how many degrees.
Basically, you have two. You have an arbitrary angle here and an arbitrary angle here. The third one is determined.
Yeah,
so these 2 angles, they become 60 degrees with non-zero bending rigidity. So those are the 2. Those 2 angles are both fixed. So we had this result for a while, but we want to check it with the numerical simulations, which Hom and Shin did. I should point out that this is part of a class of very challenging computational problems as well. Okay? Take whatever computational model you're interested in, Ising model, Potts model, ferromagnet, whatever, but put it on a fluctuating surface or an undetermined surface. Then every update of the order has to be also accompanied by updates in the geometry. There are no good global, and these are glassy-like problems, okay, with exponentially growing or very rapidly growing number of local minima and all of that. There are no really good computational algorithms when you have that, you're minimizing over the space as well as the order. No analogs of cluster moves, global moves that get you from one minimum to another and so on. At least no very good computationally efficient ones. So this is not only theoretically an experimentally challenging problem, but computationally very challenging and rich area for potential development. So we do something, very naive, okay, Monte Carlo-like algorithm, and we just basically move nodes radially along, allow them to change size and so on. But it's enough to get the idea, and a lot more could be done. So on the right, shown here, as you go across to the right, it goes to lower bending rigidity. The top row here shows the Frank free energy in the colors, and this row here shows bending energy. The red is hot or high, blue is low. You can see concentrations at the vertices. And the white lines show the director field. As you go to low bending rigidity, you see it sharpens up, becomes much more faceted. This is this 1 Frank constant case, these 2 lines, K1 equals K3, and this is K3 over K2 is 1. 2. This bottom line is K3 is 2K1. hard to realize the pure symmetric case, at least from these kinds of simulations, which are lattice simulations with a three-body term, Meyer-Selpé-like lattice Hamiltonian with a three-body term to make K3 not equal to K1. Nevertheless, you can see that it becomes much sharper in the limit of low bending rigidity. And you can plot the asphericity shown here, particularly for K3 not equal to K1 or 2. It grows quite high as the bending rigidity. This is 1 over the bending rigidity. As the bending rigidity goes low. The lowest here, this is kappa is 100, this is 0.3, and this is 0.05. And down here is kappa is 0.4, these two here. Frank energy and bending energy. So they get sharp, and you can compare. You have to be careful, but I wouldn't take this as an exact comparison, but you can look at the kinds of things they get in the experiment, which is what motivated this. So here's an experimental image, very highly faceted object. Remember, you see this only in projection. These are not 3D images. Electron microscopy images just at one view. This highly faceted object here, and we match this up with kappa 0.4 for K3 over K1 is 2. This is kappa equals 0.1. That's the one I showed you near the beginning. Okay. It looks like one face. These look like basically one face of a tetrahedron. That's what we'd like to say. As kappa goes towards 0, you should be able to get the tetrahedron. And there's the picture from simulation, from the simulation here. And this is kappa is 0.5. Get more ellipsoidal-like thing that's shown here. This one has, these things also tend to form little baby universals, budded vesicles going off here with a neck. Okay? And on the right-hand side, it's isotropic. The left-hand side, it's pneumatic or symmetric. So this has to do with kinetics of forming these things, which you've also studied. You can also get a nanotube. Okay? Remember, we had nanofiber before for the monolayer case with radius 1 over the spontaneous curvature. Here we can make a bilayer, no spontaneous curvature, but just a cylindrical solution. Now that will have the bending energy across the entire surface. So the energy will, it's a clear solution, the cylinder. You can easily rule the cylinder. It's flat. That will have an energy which grows as the area of the system, of bending rigidity times area. Whereas the tetrahedron had something that with energy that grew as the edge length, which is the square root of the area. So this tetrahedron will win for large system sizes. Square root will win over the area.
Is the tube still got the topology of a sphere? Are the caps on the ends of the tube? Is it?
You can have either. So for the limit I analyzed, yes.
So you've got ridges, so to speak, at the end of the tube, which are the end, where the ends are bolted on.
Right. But you could analyze the problem allowing two boundaries, so where the character is 0, and then you get a cylindrical solution with two ends. But if you want spherical topology, yes, it has to have spherical caps, like nanotubes. Yeah. So for length greater than a squared over b, where a is the nanotube radius, b is the radius of curvature of the ridges, they will round out in general. Above that length scale, tetrahedron wins. How about getting other polyhedra? Okay. Well, you can do that. What you have to do is vary the order. So we got the tetrahedron because we had 4 strength 1/2 defects required from the pi invariance or the twofold invariance of the pneumatic. So if we vary the order, if we have p-fold order, we're going to have 2p elementary kinds of defects required. Okay? And that will single out the vertices of some other polyhedra. So one particularly interesting case is because the order is not that much explored, and it gives something good as 4-fold order. So say you have something with invariance under rotations by pi over 2. Then that has elementary 90-degree defects instead of the 180 of the pneumatics. And you require to make up 2. So the strength of the defect is 1/4 rather than 1/2. So you require 8 of those 1/4 defects to make up 2 for the Euler characteristic of the sphere. So tetradic order on the sphere will have 8 elementary 1/4 defects. So this is very easy to do. So now you have squares, or anything with 4-fold symmetry. Take squares, tile the flat space with squares. You need 8 defects, and that's just going to fold up into a cube. And you see at each vertex, you go from here, rotate, go 90 degrees, 90 degrees again, 90 degrees again. You come back to yourself with a 90-degree deficit. So that's the 1/4 defect of tetradic order, naturally realized as the vertex of a cube. So this object, we claim, if you could build something with tetradic order, tetradic vesicle, should, in the low bending rigidity, floppy limit should spontaneously fold into a cube, which would be cool, because you can pack it 3D, exactly unlike tetrahedron, which requires dual octahedra to pack R3. If you take trivalent order, that is P equals 3, you need 6 1/3 charge disclinations. Okay, so that will give you the vertices of an octahedron with 108, 120 degree deficit angle at each vertex. Again, I'm thinking of the application of these to supramolecular chemistry. Defects are natural things to functionalize since the order vanishes there. They're distinguished places mathematically, physically, even chemistry recognizes them, and biology uses them. When you functionalize a defect, they can make bonds there or linkages. So this determines the valence of the object. So this would make the tetrahedron make a valence 4 object, sp3-like bonding. This would make valence 8 object. Trivalent would make valence 6 object. And you have hexagonal order, P equals 6. That will give you 12. That will give you back the icosahedron. So these you can all do, and you can see you can rule them also. So with a postdoc Rasko Skonetnik, we've been looking at this tetradic order. It's been studied actually experimentally by Paul Chaikin and Harrison, Russell, Hughes, and Zhao, 2007, with discs that sit on edge like this. And they have some kind of pneumatic and tetradic order. And it's been studied theoretically and computationally by Jonathan Selinger and Gang, where they study a system with a tube with a cos 2 theta kind of interaction plus a cos 4 theta perturbation. Okay? And it turns out that you can break the 2-fold symmetry quite a bit with this 4-fold order and still get this pneumatic order. Okay? So still get tetradic order. Pneumatic systems might have fairly high degree of tetradic order. Those two can coexist, in other words. We're just studying the tetradic system with the cosine 4 theta-like interaction between particles. Here shown square tiling and flat space, pavement in Rio de Janeiro. Here shown a flat space simulation and a simulation on the sphere. And squares like this with this cosine 4 theta interaction. And right here, you see a pi/2 defect. So we're keeping the shape fixed to be the 2-sphere. Then if we can understand this tetradic order and then let the shape vary, then we hope to get the cube. That's the idea.
It seems to be scarred as well in your notation.
Well, you mean here? Yeah. This is probably not completely equilibrated. But yes, this kind of order, it might also form other things, might form scars for the same reasons as crystals do. So this kind of order is not much studied. So yes, that's a possibility. Small enough system size, a number of squares, I expect you can get rid of those and just get these, but the scars would also be interesting. Very little studied system. But yes, it's either not completely equilibrated or the elementary defect might not be point-like. Something's going on here. Or it might be amorphous. Okay? Haven't completely studied the order of this yet. Typically, these systems, like the spherical pneumatic, they become amorphous. Very hard for them to order, actually. They do a lot of work to get them to equilibrate. Well, then you have tetraedic glasses. Could be interesting also. Rasko and I have also looked a little bit at these two-component systems, going back to elastic systems, not the liquid systems, but where you have two components, of soft and hard, and you vary the percentage of soft and hard things with bending energy and so on, and you can get, this is like the work they did with Monaco Vera de la Cruz. You can get lots of interesting polyhedral faceted objects here with the softer thing living along these edges. This is 3% soft, 4% soft, 4.5 and so on. Lots of possible structures. So that's even more rich. The faceting is not as surprising in this elastic case. So let me conclude. We use these rod coil, block copolymers with liquid crystalline or pneumatogen side chains in this case. You can do lots of things with these block polymers. That's why the chemists are interested in them. Lots of structure you can build into them. And all the liquid crystalline functionality you know about can be built into this vesicle. Photo response, electric response, thermal response, magnetic response, whatever. Okay? So you have control of these vesicles, and they're quite robust. We looked at the emergent structure, if you want, as this topologically spherical bilayer vesicle. The material parameters are an elastic modulus K and a bending rigidity that compete. The stiff limit, you have round or deformed round vesicles with liquid crystalline, say pneumatic or symmetric order. The floppy limit, you get faceted structures, more reminiscent of hard crystalline-like materials. Floppy limit generates these sharp structures, and if you take two-component inhomogeneous elastic systems, that's also very rich. So I'll finish there. Thank you.
In your theory, you use a covariant gradient of n.
Yes.
My question is, what would happen in your conclusion if you replace it with the surface gradient?
I mean, so what do you mean by surface gradient? Respect to the bit with respect to R3. I don't think that would change much. I think they probably agree. That would be taking the metric as the induced metric. I think it will be the same. But
You were talking about energy, so T equals 0.
yes,
No fluctuation, nothing.
at the moment, the more interesting problem is the membrane problem, from which most of the stuff came, of course. So the shape is fluctuating.
It might be to the same point, no surface energy at all. Only pneumatic elasticity and bending,
Yeah,
but no just proportional to surface area. Surface energy.
right. If you make an emulsion, you can tune the surface tension to 0.
T equals 0, I don't.
No, I mean
In reality, yes.
in the thermal case, I mean, if you're in an ensemble where you're minimizing functional derivative of F, spectral area should vanish depending on the ensemble that you take. So that's the membrane case. So if we take a micro emulsion with a symmetric at all the interfaces, that will be symmetric membrane or pneumatic membrane. And yes, so then there will be that will be fluctuating object. So here, we're determining the ground state about which this thing is fluctuating. So then there'll be some transition temperature, presumably, which would fall apart. Then if you add bending, if you add surface tension, there's like putting a tension on the system. That will typically take you away from the fixed point where you get the most interesting fluctuations, but also interesting systems. So these have been well studied, and from 70s, 80s, and so on. The reason looking here at these ground states is the ground states are these unusual kinds of ground states. And you need to know those if you want to build a theory of fluctuations on top of them. So its ground states are much richer than was anticipated.
Very, very nice. Can you say something on the role of twist, if you have twist also?
So there's no twist here because it's too deep.
Yeah, but,
So if you make it thick enough, of course, there's some twist.
then could you form sort of spiral structures?
Yes, so there are lots of possibilities once you have twist. So, I mean, it's just going to be very rich. And there are some experimental systems where you can do that. So you make it thick enough. Yeah. So that's just another axis that you have to explore. So yes, I think most things you think about. So what's going to dominate will depend on the relative Frank constants. If you make twists small compared to the others, then you'll generate maybe chiral structures and.
I didn't understand the physical situation with these bilayers. They don't interact, but somehow stick together.
What do you mean? An individual vesicle?
Yeah, how they? I mean, the assumption was that they didn't interact. Was that right?
Interact with what? No, you make single vesicle. Yeah. You mean one vesicle with another? Or the...
I don't understand what you meant by a bilayer.
Oh, I mean, okay. So, they're over here. Where's the eraser?
Yeah, I understood there were two layers, but the assumption was that they weren't interacting, right? Is that right? Because they were just...
I mean, the lipid case would be like this. Since you have, well, in our case, it's a coil and rod like this. This is hydrophobic, this is hydrophilic. These like to associate basically electrostatic interactions. So they spontaneously form this kind of structure, which is the bilayer. And so that's the interaction. The interaction is basically electrostatic. Spontaneously assembles into this bound state to put the hydrophobic places together.
Was that interaction in your model? I didn't see.
No, we're starting from a coarse-grained energy describing the assembled structure, not how it assembles. That's way too complicated for us. But it's well understood why these things form. I mean, ultimately it's electrostatics. So we're just writing a coarse-grained Hamiltonian for the single assembled structure, which is this molecularly thin vesicle. But in this plane now, the difference is in this surface, we have this liquid crystalline order. So you can get this for lipids as well, as you cool them down. They order. Lipid is actually, I mean, the most explored case here, and also very, very rich. Maybe the natural system to work, and it's just a little bit more complicated. And people doing the block copolymers because they're more robust, and you have this control over it. You can burst them and things like that. But you can do all of this with lipid bilayers.
I think actually we've got another talk going, and let's stop it there. So maybe just coming. Thanks very much.